Hello everyone, I am Abhilash, working as Assistant Professor at Department of Mechanical Engineering, Maharaja Institute of Technology, Mysore. So in the previous session on the design of machine elements, we begin with the problematic sessions on the combined loading and the conditions of principal planes and stresses. So in today's session, we will continue with the next problems. So coming for the next problem, which states that a steel member is loaded as shown in the figure. Find the magnitude of maximum normal stress and the minimum normal stress. So what they are stating is that they have given us the complete sketch, and for this particular sketch along with the loading conditions, we are supposed to identify the maximum normal stress and the minimum normal stress for the given steel member. If you clearly observe the sketch given, the one end of the steel bar, it's like a C-clamp, and the one end is completely fixed. Whereas there is an axial load which is acting at an eccentric distance of 28 millimeter. If we recall, whenever the load, the axial load, if it is acting parallel to the centroidal axis of the given member, then the type of load we are going to call it as an eccentric load. So this problem comes also under the eccentric loading condition. So the given problem is an eccentric loading problem. First, we need to resolve the eccentric load into the direct load along with the couple that is produced because of this eccentric loading condition. Along with the eccentric load, we also have a twisting moment which is the steel member is subjected for, having a load of 100 Newton meter. So first we will try to list down the given data and then we will proceed with the problem. So the data they have given is the axial load that is acting is 9000 Newton and the twisting moment that is applied to the machine member is 100 Newton meter, and we are supposed to convert this Newton meter into Newton millimeter. So that will be equal to 100 into 10 to the power of 3 Newton millimeter. Along with that, an eccentric distance of 28 millimeter, which is causing us the eccentric loading condition. So now to begin with the problem, we have identified that the given axial load is an eccentric load. So due to eccentric load, the member is subjected for both direct as well as a bending stress. So first we will try to identify the direct stress because of the axial load. Then we will identify the bending stress because of the eccentric loading. So the direct stress, we know the relation is given by sigma is equals to F divided by A. The F indicates the axial load that is acting on the machine member, that is of 9000 Newton. Whereas the area, in which area we are supposed to analyze the member. See, the given clamp is having two different diameters. One is of 100 millimeter diameter and the other one is of 50 millimeter diameter. If you look carefully into the sketch, we can identify which member is under critical conditions. So this is the fixed end and this is the load end. Because of the eccentric load and the twisting moment, the diameter of 50 millimeter or the portion which is having a diameter of 50 millimeter will be under the critical condition. So we have identified the portion of the diameter 50 millimeter and we have called it as the critical condition point. So whereas the outer surface of that particular member or the portion, we have called it as point A and B, whereas the other portion we have named it as C or D. So the critical section in the given problem is at the portion that is having a diameter of 50 millimeter. Now the area should be considered for the critical condition. So the area of a circular cross section is given by pi by 4 of d square. Substituting the values, we are going to obtain the direct stress, that is because of the axial load of 9000 Newton. So the sigma, the direct stress, is equals to 4.58 Newton per millimeter square, and this value is tensile in nature throughout the member. this value is tensile in nature throughout the member. Here only we can see the axial load will be acting along the axis and it is in the tensile direction. So throughout the cross-sectional member, this will be in the tensile nature itself. So next is the bending stress. So one is the direct stress that we have calculated now. The next one will be the bending stress. We know that in order to calculate the bending stress, the general equation is given by m divided by z, where m is because of the couple, that is load into its perpendicular distance, and the z is called as a section modulus. Depending upon the type of cross section, the value of z varies. In order to know the value of z, we can refer the table 1.3a, page number 12 in our design data handbook by Madhavan and Balvi Reddy. So if we refer this particular table of 1.3a, page number 12, we are going to get the relation what should be used for the section modulus of z. So sigma b, the moment, will be equal to force into its eccentric distance. So F into E divided by the Z value that is obtained from the table 1.3a. We are going to obtain the equation pi by 32 into d cube. If we substitute the values of the applied load, eccentric distance and for the critical section diameter, we are going to obtain the value of bending stress that is developed because of this eccentric load or the axial load. So the value that we have obtained is 18.33 Newton per millimeter square. So this is the value of bending stress that is obtained. Now coming for the cross section, here if you observe portion A and B and C and D is the critical section, and if I consider a cross section, along the member anywhere, and because of the loading condition, the portion AB will be subjected for tensile stresses, whereas the portion CD is subjected for the compressive stress because of this bending moment. If clearly we can observe, this is a steel member, because of this load, this will be the portion AB will be subjected for the tensile stress and the portion CD will be subjected for the compressive stress. So the nature of the bending stress will be tensile at the portion A or B, and it will be compressive at the region of C or D. So depending upon the condition that we are considering, it will be varying. So at the portion AB it will be tensile, at the portion CD it will be compressive. Now we have resolved the condition because of the eccentric load. Is the only the eccentric load which is acting on the member? No. Along with that, we also have a twisting moment of 100 Newton meter. So because of this twisting moment, the type of stress that is developed will be the shear stress. So we are supposed to calculate the shear stress due to the twisting moment. So the torque, given torque is 100 Newton meter, and I am converting that 100 Newton meter into its Newton millimeter. So 100 Newton, the meter is 10 to the power of 3 millimeters. So the twisting moment will be equal to 100 into 10 to the power of 3 Newton millimeter. So what is the equation for the shear stress? We know that the shear stress due to the twisting moment will be equal to the T divided by Zp, where T is the twisting moment, Zp is called as a polar section modulus. So in order to know the relation for the polar section modulus, we are supposed to refer table 1.3b in page number 14 in the data handbook of Madhavan and Balvi Reddy. If you refer the table of 1.3b page 14, we are going to obtain the polar section modulus for various cross sections. The cross section that they have given the problem is just a circular cross section. For the circular cross section, the polar section modulus is given by pi by 16 into d cube. So replacing the term 16 numerator to denominator to numerator, it is 16t divided by pi d cube. So the shear stress after substituting all the values, So tau will be equal to 16 into 100 into 10 to the power of 3, that is the twisting moment, divided by pi into 50 cube. We are going to obtain the shear stress value, and the value that is obtained is 4.07 Newton per millimeter square. Now, because of the given eccentric and the twisting moment, we have identified the type of stresses that is developed in the machine member. What is the given problem? The given problem is to identify the maximum normal stress and the minimum normal stress that is acting in the given steel member. Now we will see how to identify the maximum normal stress and the minimum normal stress using the stresses that is developed on the machine member. Now let us identify the maximum normal stress and the minimum normal stress that is developed in the portion A, B or C and D. So we have considered the critical section of A, B, C, D. In this, at first we are going to consider the portion of A, B, and at this portion let us identify what is the maximum normal stress and what is the minimum normal stress. Now at the portion A or B, before going that, this particular value indicates the value of sigma that we have already calculated based on the axial stress, the bending stress value because of the couple, and the shear stress that is because of the twisting load. So at the portion A or B, the normal stress at the portion A or B, the normal stress will be equal to the direct stress plus the bending stress. We know the reason that this particular portion of A or B is subjected for the tensile stress. It is subjected for the tensile stress, whereas the portion CD is subjected for the compressive stress. Hence, we have made use of plus sign here. If it was compressive in nature, we would have used minus. So the normal stress will be equal to the direct stress plus the bending stress. So we know the direct stress value, that is 4.58 Newton per millimeter square, and we know the bending stress value, which is 18.33. So the total normal stress at the point A or B will be equal to 22.91 Newton per millimeter square, and the tau value is 4.07 Newton per millimeter square. But we are supposed to calculate the maximum normal stress and the minimum normal stress. We know the type of loading that is acting on the machine member is of combined loading condition. So in these cases, when it is a combination of axial bending along with a torsion, or bending torsion or axial torsion, we are supposed to refer the maximum normal stress theory, which states that the maximum normal stress theory, the maximum normal stress is given by sigma by 2 plus square root of sigma by 2 square plus tau square, and this expression is available in the equation 1.a, page number 3 in the data handbook. So if we refer this particular equation, we are going to obtain the maximum normal stress equation. So the sigma max is given by sigma by 2 plus square root of sigma by 2 square plus tau square, and we know the normal stress value that we have calculated at the portion, that is 22.91. Substitute the value of 22.91 along with here also the 22.91, the normal stress, the shear stress value is given by 4.07. Substituting all the values, we are going to obtain the maximum normal stress that is developed in the portion A or B is of the value 23.62 Newton per millimeter square. Similarly, we are supposed to calculate the minimum normal stress. The only change in the equation is that the maximum normal stress equation, the plus sign is replaced by minus in order to calculate the minimum normal stress. So the minimum normal stress is given by the equation sigma by 2 minus square root of sigma by 2 square plus tau square, and we know the value of sigma as well as tau. Substitute both the values and then calculate the value of minimum normal stress that is developed in the portion A or B, and the value is minus 0.70 Newton per millimeter square. So now at the portion A or B, we have calculated the value of the maximum normal and the minimum normal stress. Now let us continue and try to identify the maximum normal and the minimum normal stress that is developed in the portion C or D. Now let us consider at the portion C or D. So this is the portion C or D. We know that in the critical section, the portion C or D is subjected for the compressive stress along its length. So this portion will be subjected for compressive stress. Hence, the normal stress sigma will be equal to the direct stress minus bending stress. So the direct stress minus bending stress. So the value of the normal stress at the portion C or D will be equal to minus 13.75 Newton per millimeter square. The sigma D value is 4.58, sigma B value is 18.33. So the sigma value at the portion C or D will be equal to minus 13.75 Newton per millimeter square. Similarly, the shear stress value is 4.07 Newton per millimeter square. Now coming for identification of the maximum normal stress at the portion C or D, we are making use of the equation, the maximum normal stress theory. So according to this equation, sigma max is equals to sigma by 2 plus square root of sigma by 2 square plus tau square. Substituting the value of sigma, the sigma value is minus 13.75, just now we have calculated the value, and the tau value is 4.07. And substituting, we are going to get the maximum normal stress at the portion C or D will be equal to 1.11 Newton per millimeter square. We know that this portion is majorly subjected for the compressive, hence the maximum stress value is 1.11 Newton per millimeter square. Similarly, the minimum normal stress, that is sigma minimum, is given by sigma by 2 minus square root of sigma by 2 square plus tau square. Substituting the value of sigma and tau, the minimum normal stress that is acting at the portion C or D is given by the value minus 14.86 Newton per millimeter square. So in this problem, we have identified the maximum normal stress and the minimum normal stress that is acting at the portion AB and at the portion CD. So we will begin with the next problem. Now, the next problem states that a point in a structural member is subjected to a plane stress as shown in the figure. Determine the normal stress, shear stress, principal stress and their directions. So far in the previous problem what we have learnt, we have taken a member which is subjected for the loading conditions and we have calculated what is the maximum stress that is developed, and in the cases of the combined loading we have understood the problems, whereas this particular problem comes under a heading of principal planes and their stresses. If we recall the definition of principal planes and stresses, it states that in any strained member, if you keep on introducing a cutting plane, we are going to obtain the normal stress and shear stress. But there are three different planes which are orthogonally mutually perpendicular to each other, in which the shear stress will be equal to 0, and those three planes will be called as principal planes, and the stresses that are developed on those planes will be called as principal stresses. And out of those three, the one that is carrying the maximum normal stress will be called as the maximum principal stress, and the one that is carrying the minimum normal stress will be called as the minimum principal stress. So we have considered a stressed member for which they have given different conditions. Along the x direction, it is acting of 30 megapascal and it is in the tensile direction. And in the y direction, the member is subjected for a 20 megapascal and it is also tensile in nature. Along with that, it is subjected for a shear of 15 megapascal. Here, there are three different type of load that is acting on the member. It is not uniaxial stress system, it is not biaxial, it is generally a plane stress system. All the stresses are acting on this particular member. First, let us try to list down the data from the sketch. So if we look into the sketch, the value of sigma x can be noted down. The sigma x value is 30 megapascal, and we know that 1 megapascal is equal to 1 Newton per millimeter square, and we are maintaining all the units in terms of Newton per millimeter square. So 30 megapascal will be equal to 30 Newton per millimeter square. Now what is sigma y value? So sigma y value is 20 megapascal and it is also tensile in nature. So it is 20 megapascal, which is 20 Newton per millimeter square, and along with that it is also subjected for a shear of 15 megapascal. So the tau xy is 15 megapascal, which is nothing but 15 Newton per millimeter square. We have introduced a cutting plane which is exactly passing through the diagonal, hence the angle is 45 degree. So whatever the angle which is 45 degrees. So the given angle is 45 degree, and remember we should always measure the angle of the cutting plane that is introduced from the vertical surface itself. By chance, if in the problem, if they have measured that with respect to horizontal, then you are supposed to minus those values. The total angle will be 90 degree. So minus 45 will give us the vertical distance value to be also as 45 degree. So if in the problem they have given the angle measuring from the horizontal surface, ensure that you have converted that to measure from the vertical face. Suppose for example, if the angle which is measured from the horizontal is 30 degree, then the total angle is 90 minus 30, this angle would have been 60 degrees. So ensure that you always measure from the vertical surface itself. So in our problem, it is they have directly given with respect to vertical surface and the angle is 45 degree. We have listed down the values and we have understood the concept of the phi angle, that is of 45 degree. Now in order to solve this type of problem, the plane stress condition, you are supposed to refer the page number 5, where we are going to get a set of equations. So we will just take the equations, we will substitute the values and then we will calculate the parameters one by one. So to begin with, the first thing they have asked us to calculate is a normal stress. So for the normal stress, sigma n is the denotation. So sigma n is given by the equation sigma x plus by 2 plus sigma x minus sigma y by 2 cos 2 phi plus tau xy into sin 2 phi. This equation for the plane stress condition is available in the data handbook equation 1.8a, page number 5. So substituting the values of sigma x, sigma y, we know sigma x is 30, sigma y is 20, and again 30, 20, and the phi angle is of 45 degrees. The tau xy value is 15 megapascal and again 2 into 45. So substituting all the values, we can obtain the value of normal stress that is developed for this particular case, and the value is 40 Newton per millimeter square. So the first parameter what they have asked us to calculate is to calculate the normal stress that we have calculated, and the value is 40 Newton per millimeter square. Now the second thing they have asked us to calculate is a shear stress. A similar way we are supposed to identify the relation for the shear stress, substitute the values and get the what is the value of shear stress. So the shear stress tau normal is given by the equation sigma x minus sigma y by 2 cos 2 phi minus tau x5 into sin 2 phi, and this equation is available in the data handbook equation 1.8b, page number 5. So this is for a plane stress condition. It is subjected for all three type of stress conditions. So we are making use of a plane stress condition equation. So substituting the value of sigma x, sigma y, tau xy. So sigma x value is 30, sigma y value is 20, phi angle is 45 degree, tau xy value is 15, and again phi value is 45. We are going to obtain the normal shear stress that is developed in the particular member, which is of 5 Newton per millimeter square. So we have calculated the value of normal stress as well as the shear stress. Now let us try to calculate the value of principal stresses and their directions. Now Coming for the calculations of the maximum principal stresses, that is denoted by the term sigma 1. So, we have an equation in order to calculate the maximum principal stress when the member is subjected for a plane stress condition. The equation is given by sigma 1 is equals to sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 whole square plus tau xy square, and this equation is available in the data handbook page number 5 under equation 1.8c, and we have listed on the values of sigma x, sigma y and tau xy as well. So, just substitute the values and then calculate what is the maximum principal stress that is developed in the given plane stress condition. So, the value is 40.81 Newton per millimeter square. So, this is the maximum amount of normal principal stress that is developed for the given condition. Similarly, we are supposed to calculate the minimum principal stress that is denoted by the term sigma 2. So, the minimum principal stress is denoted by the term of sigma 2. So, the minimum principal stress equation is given by sigma 2 is equals to sigma x plus sigma y by 2 minus square root of sigma x minus sigma y by 2 square plus tau xy square, and it is available in the equation 1.8d in the page number 5. And substituting the values of sigma x, sigma y and tau xy, we can get the value of the minimum principal stress that is developed for the given condition. So, substituting the values of sigma x, sigma y, tau xy, we are going to obtain a value of 9.18 Newton per millimeter square. So, this is the amount of minimum principal stress that is developed because of the given stressed condition. Now, we are supposed to calculate the directions in which the principal stresses are acting. So, in order to calculate the directions of principal stresses, we have a direct equation that is given by tan 2 phi 1. This indicates the angle at which the maximum principal stress is acting. So, tan 2 phi 1 is given by 2 tau xy divided by sigma x minus sigma y. So, this expression is used in order to calculate the direction of principal stresses, and this equation is also available in the data handbook in the page number 5. So, for the plane stress system, whatever the given conditions in the problem might be, whether it is a normal stress, whether it is a shear stress, whether it is a maximum principal, minimum principal, just look into the equation page number 5 under which there are many equations corresponding to the given conditions. Take the equations and we can proceed with the problem. So, now coming for the calculation of direction of principal stresses, we have tan 2 phi 1 is equals to 2 tau xy divided by sigma x minus sigma y. So, now we are supposed to calculate the value of phi 1. So, tan 2 phi 1 is equals to 2 into, we know the tau xy value to be of 15 and sigma x value is of 30, sigma y value is of 20. What I want is phi 1. Just substitute the value of tan inverse and then divide it by 2. We are going to obtain the value of phi 1 to be 35.78 degrees. So, the maximum principal stress that is acting at having a magnitude of 40.81 and it is at an angle of 35.78 degree in the given condition. Then what will be the other value, that is phi 2? We know that the phi 1 and phi 2 will be at 90 degree apart. They are mutually orthogonal to each other, principal planes. So, the phi 2 will be equals to phi 1 plus 90 degree. So, what is the phi 1 value? The phi 1 value is 35.78 and 35.78 plus 90 degree will give us the value of 125.78 degrees. So, we have calculated the angle also in which directions they are acting. So, in the given problem we have calculated the normal stress, shear stress, the principal stresses and their directions. In a similar fashion, if in the examination the load conditions might vary, here all the loads are acting in a tensile direction itself. this might be even in the compressive direction. Then the only thing that changes are sigma x value will be in terms of minus if it is a compressive load. Similarly, sigma y will be in the negative sign, that is minus 20 if it was an compressive load. So depending upon the nature of loading, we are supposed to take the value of sigma x and sigma y and then continue with the problem. So in all the problems in a plane stress condition, they are going to ask the questions in a similar fashion. Try to analyze the sketch, note down the values, ensure that always we are going to measure the angle from the vertical surface itself, not from the horizontal surface. Measure the angle from the vertical surface and then continue with the problem for the given conditions. So this concludes the numerical sessions on the problems on the combined loading and the cases of principal planes and principal stresses. Now let us see a very important factor, that is the factor of safety. The factor of safety plays a very important role in the design aspects. So hence, as a mechanical engineer, specifically when we are looking for the design field, we should be thoroughly understanding the terms or the concepts with respect to the factor of safety. See, while designing any component for that matter, we should provide some amount of reserve strength in order to avoid the accident or the failure of a component. So that is provided with the help of the term called as factor of safety. Now how do we define this term factor of safety? The factor of safety or FOS is defined as the ratio of maximum stress to the working stress. So I'll repeat the definition again. It is defined as the ratio of maximum stress to the working stress. A factor of safety is denoted by the term N. So N is equals to the maximum stress divided by the working or allowable stress. What is the maximum stress for any material? If it is a ductile material, it will be the yield strength. If it is a brittle material, it will be the ultimate strength. So that we are going to consider it as a maximum stress. We all know that if a material reaches the plastic state, we will be considering it as a failure. If not, in some cases, if it reaches the yield strength, then it is considered as a failure of that particular member. What if it is a brittle material? If it reaches the ultimate strength, it will be called as a failure. So we should ensure that particular material or the component that we are designing will be not able to reach that ultimate or the yield strength. For that reason, we are supposed to provide some amount of reserve strength utilizing the concept of factor of safety, or it can also be defined as the failure load divided by the working load. This factor of safety is a dimensionless quantity. It is just a number that indicates that this amount of factor of safety is applicable for that component, or this amount is required in order to ensure the safety of a material. Then what is this new term which is called as an working or allowable stress? See, this working or allowable stress is very important in the design concepts that determine the dimensions of the machine component that we are designing. The allowable stress is defined as for the ductile material as the ratio of the yield stress to the factor of safety. So for the ductile material, the allowable stress will be equal to the yield stress divided by the factor of safety. Similarly, for the brittle material, the allowable stress will be equal to the ultimate stress divided by the factor of safety. So basically, the allowable stress is the safe stress, where the design engineer ensures that if it crosses this allowable stress, the material will be undergoing the failure. So we should ensure that it will be well within this allowable stress. We know that the material should reach the maximum or the failure load in order to fail, but we are providing some amount of reserve strength in order to avoid the failure in some cases. Like if some accident occurs, if failure occurs, if there is a sudden impact load. So that has to be sustained by providing some amount of reserve strength that could be done with the help of factor of safety, and hence as a design engineer we should always ensure that the stress is designed based on the allowable stress. See, there are number of design analysis that we carry out in order to ensure the safety of a component. But while designing or while making that analysis, there are number of uncertainties. For example, in order to make the calculation easier, we would have assumed some of the parameters, or the component after manufacture might be of some amount of defect because of imperfect workmanship, or the material could be itself inhomogeneous in nature. So there are certain conditions that we cannot predict. So in all the cases, to ensure all these uncertainties, the factor of safety plays an important role. Then can we choose the factor of safety very easily? No, we cannot choose the factor of safety value so easily. There are number of parameters that determines the amount of value to be chosen as the factor of safety value, but always ensures that the value should be greater than 1. I will explain it why it should be greater than 1 at the later part. Then what are the parameters that is essential in order to consider the factor of safety? So the selection of factor of safety, it depends upon the type of material, type of load, the homogeneity of the material, the working conditions. So there are number of parameters that determines the selection of a proper factor of safety for the designing aspects. Let us try to understand what will be the factor of safety value under these circumstances. The first condition that we have taken is if there is any variation in the material property. For instance, if we consider an homogeneous material, let us take an example of steel itself. Steel is an homogeneous material. In that cases, the residual stresses will be lesser in the component. So under that circumstances, whatever the factor of safety value that we are choosing can be of lesser in amount compared to that if it is of inhomogeneous material. For instance, the cast iron. If you are making use of a cast iron, in order to design a component, we should ensure that there will be large amount of residual stresses that are stored. For that reason, we are supposed to provide a factor of safety value of higher in nature. It should not be lesser in nature. So depending upon the homogeneity in the material, whether it is an homogeneous material or an inhomogeneous material, we can choose the factor of safety. If it is an homogeneous, the value of factor of safety will be lesser in nature. If it is of inhomogeneous, the factor of safety value will be higher in nature. The second parameter is depending upon the type of loading and the stresses that is developed. If we know if the material component is subjected for a static loading condition, we know that it is a fixed one. There will not be any extra load that will be acting on the machine component. In such circumstances where there is only the static load that is acting on the machine member, the value of factor of safety can be taken at a lesser number. Whereas on the contrary, if there is an impact load that is acting on the member, if there is an impact load that is acting on the machine component, then the value of factor of safety should be of higher in nature. Just in order to ensure the safety of that component, whenever there is an impact load acting on it, we should take a factor of safety value little bit higher. Now, the next is based on the degree of accuracy in force analysis. While doing the design analysis, if we consider all the forces that are acting on the machine member, or if you are thoroughly analyzed, these are all the forces that are acting on the machine member in both working condition and as well as in the design state, then we can consider the factor of safety value of lesser in nature. And if you are uncertain about the forces that might act on the component, then the factor of safety value should be of higher in nature. So if you are thoroughly analyze the forces that are acting on the machine member, then we can choose the factor of safety value to be of lesser in nature. If it is of uncertain, then we are supposed to go with an higher factor of safety value. The next is depending upon the quality of manufacture. If we are manufacturing the machine component with high precision accuracies, then the factor of safety value might be of lesser in nature. If it is of imperfection in the work that is manufacturing happening, then we are supposed to ensure that the factor of safety value should be of higher in nature, just in order to ensure the safety of the component. So depending upon the quality of manufacture, the factor of safety value relies. If it is perfectly accurate while manufacturing a component, then the factor of safety value could be of lesser in value. If it is of not accurate, then the factor of safety value should be of higher in nature. The overall concerns for the human safety plays an exemption role while selection of a factor of safety. See, the overall concern for the human safety, in other words, we can say that on what conditions the machine components are operating. If it is of pressure boilers in nature or pressure vessels for that matter, the factor of safety value should be of higher in nature, because the human involvement, the workers will be working in that particular environment for a longer period, and if that failure happens, the cause of is havoc. So hence, while designing a pressure vessels, boilers, hoist drums, cranes, we should ensure that a higher factor of safety value should be taken care. Though depending upon the human safety requirement, the value of factor of safety should be dependent. The service conditions plays a significant role while selecting a factor of safety. On what atmosphere the machine component that we are designing are functioning, whether it is in a corrosive atmosphere. So depending upon the atmospheric conditions, we are supposed to choose a factor of safety value. So this service conditions also plays an important role while selecting a proper factor of safety value. So far these are the parameters that are few of the parameters that are essential in order to choose the factor of safety value while designing any component. We are discussing only in terms of whether the value should be of lesser or higher. What happens whenever the value of factor of safety increases? So whenever the factor of safety value increases, the size of the component increases, the dimension of the component increases, the cost of the component increases. So we should ensure that we should not take the value randomly. It should be appropriate value. By considering all the parameters, we should take the factor of safety value properly. Now, in the beginning itself I told why it should not be less than 1. It should be always greater than 1, because we are designing any component based on the allowable stress. If the allowable stress is of higher compared to that of the maximum stress, so the factor of safety value will be in terms of point something, which is ensuring that the material is not safe, or the maximum stress itself is less compared to that of an allowable stress, which will eventually lead for the failure of a component. Hence, ensure that always the factor of safety value should be greater than 1 while designing any component. So this is about the significance of factor of safety. In this session, we have understood the concepts on the numericals and combined loading and principal planes and stress conditions, along with the factor of safety and what are the parameters that are essential in order to select the proper factor of safety. Thank you.